Okay, now we're starting to see it here. Are you ready? That's going to give me an echo. I don't want an echo. Okay, so now we're recording. Okay. So rotational motion, angular momentum. Let's talk about what angular momentum is. We've already talked about torque, and we've talked about these relationships between linear motion and rotational motion. So the angular momentum is obviously related to linear momentum. Why can't I close this thing? Every time I close it, it opens again. It's like it's behind first. Okay, it's now working. So anyway, we're doing angular momentum now, and we're going to start off with angular kinematics essentially. So instead of having linear velocity, we have angular velocity, which we've already talked about. So angular velocity being omega, which is the change in angle over change in time. If you go through a certain amount of angle in a certain amount of time, that's called angular velocity, omega for that, right? And the relationship between the angular velocity traveling around a circle, omega, and the linear velocity along the edge of that circle, the linear speed along the edge of that circle here with a radius r, is the linear velocity v is equal to the r, the radius of the circle, times the omega. And so you can actually twist that around and make it omega equal to v over r. And we've seen this before already. And then angular acceleration, or the change in omega over change in time, or the change in angular velocity over change in time, we call alpha right there. And so we can go ahead and use the same kinds of equations that we did before with linear kinematics and use them for rotational kinematics. In this particular problem, we have a teenager puts her bicycle on its back, starts the wheel spinning from rest to a final angular velocity of 250 RPM in 5 seconds. So RPM is rotations per minute, but when we're dealing with omega, we want to deal with radians per second. And so we need to switch that to radians per second. Well, RPM rotations, one rotation is 2 pi radians. And per minute, of course, is every minute or every 60 seconds. So we need to make a conversion. And that's exactly what we're going to do right here. We have the 250 revolutions per minute, or rotations per minute, however you want to call it. And we're going to convert that to radians by multiplying by 2 pi radians for every revolution. The revolutions will cancel. We'll just get 2 pi radians per minute then. And then 1 minute for every 60 seconds, so that the minutes cancel out and we're left with radians per second. Turns out to be 26.2 radians per second. And then the definition for alpha is the change in omega over the change in time. Well, this is the change in omega, 26.2 radians per second, because that's the final omega, and we started with a 0 omega, so the final is the change, the total change. And the time that it took was 5 seconds in this case, so we get 5.24 radians per second squared of angular acceleration. Now, in this problem, they also want to know the time it takes to stop something if we have a certain acceleration. So the acceleration that we're going to stop with is given to be negative 87.3 radians per second squared with brakes. And our omega is our change in omega is going to be from that top speed of 26.2 radians per second down to 0, which will give us a change in omega of negative 26.2 radians per second instead of positive, because we're going from the positive 26.2 down to 0. So that's a negative change. And you just take those, divide them by each other, and it takes 0.3 seconds to stop the wheel. And we get all that just from rotational dynamics. We don't know how far the bike went. We don't know how fast it was going on the ground. That would all depend on the radius of the wheels. For a bigger wheel, the bike would have been going faster and sped up faster and slowed down faster. For a smaller wheel, it would have been less. So the acceleration, of course, along the edge of the circle, if you're moving in a circular path like this, is going to be different because it's a tangential velocity v and a tangential acceleration, right? And also we have to talk about the acceleration that keeps it going in the circle, which is the centripetal acceleration, which goes towards the center of the circle. So we talk about all these things to calculate our accelerations. To calculate our tangential acceleration, we need the change in the speed along the edge of the circle times the change in time, which is going to be equal to the change in the radius times omega, where the omega is the thing that changes, so the radius comes outside that delta. We're left with this equation. And the tangential acceleration equals r times delta omega over delta t, but delta omega over delta t has a definition, which is the acceleration, the angular acceleration. So the angular acceleration times r equals the tangential acceleration. And we start to see a pattern. Every time you want to get a tangential value for something, the distance that you travel along the edge of the circle, or the tangential speed along the edge of the circle, the tangential acceleration along the edge of the circle, you just take the rotational counterpart and you multiply by r. So this one, you take the rotational acceleration, alpha, multiply by r, and you get the tangential acceleration. You do the same thing with the radial or the rotational velocity, or the angular velocity, omega, multiply by r, and you'll get the tangential velocity along the edge of the circle. You do the same thing, and that's this one right here. R times omega gives you tangential velocity, which is this one here. And if you want to know the arc distance, or the distance along the edge of the circle that you travel, then you just take the angle that you moved through, the angle that was rotated to give you that arc, and multiply by r, and it'll give you the length of that arc, or the distance along the edge of that circle. And we've talked about that before, those relationships, but we're going to use them a lot more now. So here we have a motorcycle is going from 0 to 30 meters per second in 4.2 seconds, and we want to know the angular acceleration of the wheels if the radius of the wheel is 0.32 radius, 0.32 meters. So we are given the tangential acceleration, which is a sub t, and that's going to be delta v over delta t, which is 30 over 4.2. We're not given a tangential acceleration, but we're given the delta v over the delta and the t. So we can plug those numbers in and calculate the tangential acceleration to be 7.14 meters per second squared. Well, of course, the tangential acceleration and the radial acceleration are related by this relationship where we multiply the radial part, or we multiply the rotational part times the tangential part. And if we rearrange that, we get that the rotational acceleration equals the tangential acceleration divided by r. So we just divide by r to get back to radial, to get back to rotational. And it's 7.14 divided by 3.320, and it's 22.3 radians per second squared for the angular acceleration. And so here you have all of these different things that we use in different types of kinematics: rotational kinematics, translational kinematics. We have angle in rotational, and we have distance in translational. We have angular velocity in rotational, we have linear velocity, and we have angular acceleration and linear acceleration. And the relationships between these two are all just to go from linear to angular, you divide by r. To go from angular to linear, you multiply by r. Quite simple. So now we have to decide on how to determine the directions of these things, because of course rotational velocity, rotational or angular velocity, angular acceleration, and they are actually going to be vectors, just like all other vectors we dealt with, all other velocities and things. So in order for them to be vectors, they need to have a direction, and so we need to decide on a direction. And again, kind of like with the torque, we're going to use a clockwise, counterclockwise kind of thing to determine the direction. So an angular velocity, for example, that as you're looking at it rotates in a counterclockwise direction, we'll usually call negative. And it's a little more complicated than this in real life, but this makes it easier for us to teach it and learn it at first, and you'll learn more about it later as you move on. And then, of course, the clockwise direction is negative. Counterclockwise positive, clockwise negative, and we'll use those standards for now. So kinematics. Kinematics, very much the same as linear kinematics. We have these equations, and you can see that the computers kind of messed these up a little bit. Hopefully they're looking better on your computer. I'm using an older computer right now. But you have these same equations that we can use, and you can combine them to learn things. And then you can use the equations that we had on the previous page that relate the tangential and the rotational to go back and forth between both sets. So you can do problems that involve both types of kinematics together. For example, we have a deep sea fisherman. They hook a big fish, pulling away from his fishing reel. The whole system is initially at rest. The fishing line unwinds from the reel, and the reel has a radius of 4.5 centimeters, and it gives an angular acceleration. The reel is given an angular acceleration of this 110 radians per second squared for 2 seconds as they try to reel it in, right? And they want to know the final angular velocity of the reel, which we'll use kinematic equation to do, and then the speed that the fishing line is leaving the reel. So that's essentially the speed of the fishing line. That's a linear speed, so you have to convert to a linear speed from the angular speed along the outside of the reel. How many revolutions does the reel make, and so on and so forth. So lots of things to figure out, and it's not necessarily easy to do it, but it's pretty straightforward as long as you keep things organized. So the first thing we're going to do is you can use a kinematic equation, this one right here, the final angular velocity equals the initial angular velocity plus the angular acceleration times time. So that's angular acceleration alpha, not a. And we know that its initial is 0 and its final is 110, or is, we also know that the acceleration is given at 110, right? Is that what it was? Yeah. It gives us an acceleration at 110 radians per second squared for 2 seconds. So the initial plus the 110 times 2 seconds, it gives us a final of 220 radians per second of reel going out there. And then what happens after those 2 seconds? After those 2 seconds, what is the speed? Right? The speed of the wire going off, the string going off, is the tangential velocity equals r times omega. That r is the same r that we haven't used yet, actually, but that's given above. And it turns out it's 0.045 meters and 4.5 centimeters, in other words. We multiply that radius times the angular velocity, and we get an actual linear velocity that the line is coming off at 9.9 meters per second. And then in C, we want to find the number of revolutions. Well, the number of revolutions is going to be determined by the amount of angle that it goes through. For every 2 pi radians of revolution, 2 pi radians of rotation, you're going to get 1 revolution, right? So we have the theta, the final theta is equal to initial theta, which is 0 in this case, plus omega, the initial omega times t, which is also 0 because the initial omega is 0. And then plus 1/2, actually this is it, yeah, plus 1/2 times alpha, so there's your 1/2, there's your alpha, your angular acceleration, times time squared. We have times 2 squared here. We get 220 radians. Well, how many rotations is 220 radians? Well, you take that 220 radians and divide it by 2 pi, and you get 35 total revolutions. So in that short time, you get 35 revolutions. And how much fishing line is going to come off in that case, in that amount of time? Well, the amount of fishing line is a linear measurement, and that's equal to r times the angular measurement. So how much angle did it go through? 220 radians. What is the r? 0.045 meters. Multiply those together, and you get 9.9 meters of string that comes off linearly, as if you unwind it into a long line. And that's how it goes. So the next thing that we have to do is we have to talk about why. Well, I'm going to leave that off for now. I'm going to move on to dynamics of rotational motion and do angular momentum later. I'm going to stop this video right here so to make sure that it works, and also make sure that I don't bog down the internet as I upload it. So this will be just the first recording of a few. 14 minutes long is not a bad recording.